right. Hello, everyone. Thanks for joining me. My name is DK. I've been working through a series on the Sum-of-Divisors function. And I keep thinking that I'm going to be done with this topic, but I keep finding new things to talk about. So I'm going to keep going until I run out of things to say. So I feel like this one is, what we're going to just do today is we're going to discuss the rules that govern the multiplicative form of the Sum-of-Divisors function. So I'm going to explain that in a minute, but you're not going to find this on Wikipedia. So that's why I'm putting this up here, because I think this is really valuable to understand, and yet there's almost no information about this. So without further ado, let's just get into it. And the keys that I want to go back to kind of is I'm going to be focusing on discovery, exploration, and understanding, right? That's what we're going for. So I'm not going to be proving anything. I'm just going to be exploring. So hopefully this helps you understand the Sum-of-Divisors function. It's such a simple function, and yet what it really shows is that what I've figured out and discovered, is that there's a lot of things that are impacting how it works and how it functions. So I found this really interesting. I hope you do too, because again, I have seen nothing discussing this explicitly. So we're going to be discussing the rules governing the multiplicative form of the Sum-of-Divisors function. So in case you're not aware, really quickly, the Sum-of-Divisors takes a number and then looks at all the divisors of that number, adds them up, and then produces a result, a sum, right? So all the divisors of 1 are 1, and so it's just 1, right? The divisors of 2 are 1 and 2, so you add them together and you get 3. The divisors of 3 are 1 and 3, so you get 4. The divisors of 4 are 1, 2, and 4, so 1 plus 2 plus 4 equals 7. Divisors of 5, which is a prime, is 1 plus 5, which is 6. The divisors of 6, our first perfect number, which we've talked about a lot ad nauseum, is 1 plus 2 plus 3, which is 6, plus 6, which is 12, right? And then we have 7, which is a prime, so 1 plus 7 is 8, and so on and so forth. So I want to point out really quickly, I want you to notice and observe a few things, and that is, if you look at this list, it's not very intuitive. There doesn't seem to be much going on here that it makes sense, right? We have 1, and then we have 3, and then we have 4, and then it skips to 7, and then goes back to 6, and then 12, and then back all the way up to 12, then goes down to 8, then 15, then back to 13, then up to 18, right? So you have this all over the place pattern. It's not a pattern, right? It's all over the place. So it's very difficult to see what's really going on here. So one of the first things that I did is I took these outputs. I looked at the first 100 numbers, right? When n is 1 through 100, right? And looked at the sum of their divisors. And what I found is that what I did was I took all these outputs and I organized them. I arranged them, right? One of the best ways to approach something in mathematics is to look at it systematically in some kind of logical order, right? Some kind of systematic way, a methodical way is a good way of putting it, right? And so what I did is I took the numbers and I put them in order of lowest to highest, right? So what I saw that was, of the possible positive integers that the sums could be, we only actually get 41 below 100. So there's a lot of numbers, the higher up numbers, right, between 1 and 100 that are above 100. But below 100, we get this set of numbers, and there's only 41 numbers. So remember, you have 100 inputs. So theoretically, in my head, I was like, okay, you're probably going to have about the same amount of outputs, right? So if you have 1 to 1, there's always a 1 to 1 in a function, right? It's a 1 input, to one output. But what we find is that some outputs repeat, and then some outputs are much greater, are much higher up than the number itself. So with that in mind, we get this list of numbers. And what I want you to notice is that even when we do this and we organize in some systematic way, we still really don't see much of a pattern, anything that really governs it, right? So I'm just going to point out really quickly, we have our perfect numbers, or the sum of our perfect numbers, the sum of the divisors of our perfect numbers are here, right? 3 times 4 will get you 12. Then we have 7 times 8, right? Will get you 56. And look at that, we have that number. And then we have, so these two, the multiplication of these two gives you 12, 7, 8 is 56. And then we have 31 and 32, right? Will get you, well, it's a number that's out of this list, but it'll get you 992, right? Which is in the set of all sums produced by the Sum-of-Divisors function. And before I continue, I want to highlight one of the most important things to understand when dealing with really any function, but specifically with this one that I found, is we must be very precise about what set of positive integers we're dealing with. Are we dealing with the set of all positive integers, that is the inputs into the function, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to infinity, or are we dealing with the outputs of the function? And as you can see, as I already mentioned, there's a lot of positive integers that are missing. So this becomes a problem because there are odd things that happen with this, right? And before I delve into that, let me go back to here for a second. We're going to talk about the two primary forms of the Sum-of-Divisors function. So the one that I've described and defined is the base definition, the additive form. And that is defined as, mathematically, as the sigma of n, right? Sigma of n, where n is a positive integer. And we write this as the sum of the divisors, where d is the divisors of n, right? So whatever the n number is, so let's say it's 6, we add up the divisors of 6, right? Divisors of 6, that's what we add up, and we get the exact precise sum every single time, right? As long as we have all the divisors, we do it. Now, it turns out that the Sum-of-Divisors function is what is known as, has another form, and that is, it's called a multiplicative function, or form, and that means something important. And so what I'm going to do really quickly is express an example, right? It's a generalization. So we have sigma of n, the Sum-of-Divisors of a positive integer n, looks something like this, where we take n and we split it up into what we call our coprimes. That means each one of these numbers is built off a separate prime. And this will equal sigma of A times sigma of B. Now, I'm not going to go into examples right now because I've already made multiple examples. I've talked about the multiplicative form. I have an entire episode, series, section on the multiplicative form. So I'm not going to delve into it, but this is the basic form, right? And what I discussed actually in the previous two videos was that I will define really quickly for precision, right, where A and B, this becomes important, and B are coprimes. In other words, A must be made up of one prime, and B must be made up entirely of another prime. Now you can have multiple coprimes, so it becomes powers of primes is what it actually becomes when you break it out. And we're going to explore that later, so don't worry too much if that doesn't make sense right now, right? But the important part is that you do understand this, because this is going to be a concept that we're going to go back to. And so as I thought about this more and more, I realized that the idea behind multiplicative form, well, what do we know about multiplication? Well, there's a rule that governs all multiplication. And this is, so we can actually define this as all multiplicative functions, all multiplicative functions are governed by the fundamental theorem of arithmetic. Whenever we see multiplication, we immediately know that it is governed by the fundamental theorem of arithmetic. Now that is one really long sentence that sounds overwhelming, but if you're familiar with it at all, it's very simple. The definition of that is, right? So, and that is, I will write that out, is every integer, every positive integer, I'm going to say positive, integer, well, every positive integer, or you can say every integer greater than 1, positive integer greater than 1, which it's implied, I suppose, if you say greater than 1, you know that it is going to be a positive integer rather than negative, can be factored, uniquely into prime numbers, or into powers of primes. Powers of primes. So every positive integer has a unique factorization that is unique to itself and only itself. It gets no other number, right? So this is an important concept, an extremely important concept. And I want to pause and emphasize again one more time that this rule governs not just the sum of divisors function, which we've proven to be multiplicative, but all multiplicative functions, right? So I'm highlighting this because I want you to remember and think about this. If you're dealing with a function that is multiplicative, then, and you're stuck on a problem or stuck on something, consider that multiplicative functions are governed by the fundamental theorem of arithmetic. And see where that leads you. Explore that idea and see if it gives you understanding that you might not have had previously. For instance, again, let's go back to the set of all sums produced by the sum-divisor function, right? What we're saying is that these numbers are somehow governed by this rule. But that doesn't seem like it. On the surface, it really doesn't look like that, because we have things like I pointed out, 3 times 4 is 12, great, okay. So we see that sometimes 8 is 56, great. But then we have things like 20, which we have 4, but which is 4 times 5, but 4 exists, but 5 doesn't. So why does 20 exist? And for that matter, why does 40 exist, right? Which is, this is 2, 4 times 5, and this is 8 times 5, right? So that doesn't make sense because 5 doesn't exist, right? And then we have things like the prime number 3 and the prime number 7 exist. And so you would think that 3 times 7 would generate 21. That's what the multiplicative form tells us. The fundamental theorem of arithmetic, is telling us. And yet, we don't get that. So what's going on here, right? So this is where it took me a long while to get to this point, but I finally questioned why these numbers seem so random. They don't seem to follow any rules according to the multiplicative form, right? The additive form made complete sense, right? You add the numbers, and this is the number you get. But interestingly enough, the multiplicative form implies that this rule should be followed as well. So let's take a look at this. This is really fun because what we find is that there are contradictions, but they actually all work together. So the first thing we're going to do, I found that there are 4 rules that govern the Sum-of-Divisors function. Now there may be others, but these are the 4 that I found. So again, spirit of discovery, let's look at the 4 that I discovered. So what I first want to do is actually look at the first prime that's missing. I've been harping on this idea that the identity for perfect numbers within the Sum-of-Divisors function, which is sigma of n is equal to 2 times n, is invalid, is logically invalid, right? Because 2 does not exist here. And so let's start our first rule. I want to make our first rule based off this missing prime, right? So rule number 1. So we're going to say rules. And we're going to say number 1. For any prime number, P that is not an output, I'm going to run out of space. I don't want to do that. Not an output of the Sum-of-Divisors function. Sum-of-Divisors function. I'm going to be a little bit redundant and repetitive so that I make sure we're very clear on what we're talking about. Okay. Powers of P, the prime number, will not exist. All right? So, let's check, right? Checking. So let's go for 2 to the k, right? Let's go 2 to the 1 is equal to, does not exist. So that, so what we're going to do is 2 to the 1, does it follow the rule? So 2 to the 1 doesn't exist, follows the rule. Great. 2 to the 2. 2 to the 2 is 4. Well, that doesn't follow the rule. And we've got 2 to the 3. Well, that doesn't follow the rule. 2 to the 4, that follows the rule, okay. 2 to the 5, that doesn't follow the rule. All right, and 2 to the 6, that follows the rule. All right, so it seems to me, and actually I'm going to do 2 to the 7. 2 to the 6, by the way, is 64, so right, so it doesn't exist. And then 2 to the 7 would be 128, and that doesn't follow the rule. It's out of the list, but trust me, it's there if you want to double check. By all means, actually, don't trust me. Double check me, right? To err is human. So if I may mistype something or miswrite something. It's a lot of times correct in my head, but it's incorrect when I write it down, or vice versa. I may be making a mistake. Please call it out and let me know. So, right out of the gate, we have a problem. Our first rule is not making any sense, right? So, what I want to do is really quickly, let's observe closer, right? So let's look at the ones that break our rules, at the numbers that break our rules, right? So we have 2 to the 2 is equal to 4. We have 2 to the 3 is equal to 8. 2 to the 5 is equal to 32. And 2 to the 7 is equal to 128. Now remember, we're in the sum-of-divisors function, right? So what do we know about all of these numbers? Let's look at the context. Consider context. Consider context. Now, if it's not obvious just yet, hopefully it is already, every single one of these numbers is preceded by a prime number. And it turns out, within the sum-of-divisors function, there is an identity for prime numbers. When we have a prime number as n, when the n, the positive integer, from the set of all positive integers, right? So the input side of the function, when that input is prime, the output is simply plus 1. So what we see here is that all these numbers exist in spite of the fundamental theorem of arithmetic, the rule, because the number right before in the set of positive integers is prime. Remember, this is the outputs of the sum-of-divisors function, but in the set of positive integers, it's the inputs. So it happens to be, prime identity. So we're going to say these sums, so when we're looking at the sum-of-divisors function as a multiplicative function, these sums exist because of the prime identity. Which is this, sigma of a prime is equal to the prime plus 1. Now, if we consider, so we need to amend our first rule. So instead of a period, we say, except when p to the k minus 1 is a prime number for some integer k. So I already presented this rule previously, but what we understand here all of a sudden is that although we have the multiplicative form and that it does follow the fundamental theorem of arithmetic, the prime identity supersedes, overrides this rule and creates outputs, products, in this case products, that shouldn't exist, but they do. Thus we have powers of 2, such as 4, 8, and 32, which happen to be very related to perfect numbers, interestingly enough, right? And then right before them is a prime of prime. And what's interesting about that, notice too that those primes exist. Both of the factors of perfect numbers exist within this set. Now, let's look at the number 5, right? So the next prime that's missing is 5. If you notice, 5 to the power 1 is missing, but then 5 to the power 2 is 25. Well, that's missing. 5 to the power 3 is 125, and that's missing. And if you notice, if you think about it, 5 to the power of 2 is 25, minus 1 is 24. Well, 24 exists, but 24 is not a prime. So 25 doesn't exist. The prime identity does not override powers of 5. In fact, the prime identity does not override powers of odd primes. Prime identity does not supersede, I'm going to say supersede, the powers of odd primes. So this is something to understand, right? Let's look at rule number 2. Okay, I'm gonna have to erase this, and we're gonna have to do 2 parts, which is fine because they're actually kind of separate. Okay, so let's consider the next rule. I'm satisfied with our first rule. It feels like it actually works, right? And you can check this with other primes. For instance, the 11, right? Power 11 does not exist. And 11 to the power 2 does not exist. And 11 to the power 3, right? So, rule number 2. Okay, so then the next thing I want you to notice is that for any pairs of primes that are not, so we're focusing still on missing positive integers here. We have another rule. I'm just going to write it out. For any pair of primes that are not outputs, the sum of divisors function the composite product n, will not exist. Okay? Again, this is based off of the fundamental theorem of arithmetic. If we don't have our powers of primes, then we don't have what we need, right? But that's interesting. It's considered 20, right? Let's check. Let's look at 20. 20 has the factors 2 to the power of 2 times 5 to the power of 1. Now let's break it all up. 20 is equal to 4 times 5, which is equal to 2 to the power of 2 times 5 to the power of 1. Okay. So 2 to the power of 2 is 4. We actually have that, right? We have that. We have that factor, but we don't have 5 to the power of 1. It's not. So how does this possibly exist? Well, again, context. Turns out, what's right before 20? 19. And 19 is a prime. So once again, we have the prime identity interfering, superseding, I should say, the fundamental theorem of arithmetic. And let's look at 40, right? Let's look at 40 though. 40 is equal to, let's see here, 8 times 5, right? 8 times 5, which is 2 to the power of 3 times 5 to the power of 1. Now, what's right before 40? 39, right? Now, what do we know about 39? 39 is not a prime. So what's going on here? Why does this number exist? Well, the easiest way to figure that out is to look at, is reverse engineering this, right? So if we can't explain it by context, then let's reverse engineering. Right? So we have something like sigma of A so we have, again, sigma of A is equal to 8, and we should have a sigma of B is equal to sigma of 8, sigma of B is equal to 5, right? Why am I not doing this right? That is not correct. I'm sorry. Give me a second. thing is, what happens here? 40 is derived from the powers of a prime, and the powers of a prime is, I know how to do it, I just don't know why. Derived from power of a prime. And real quick, I'm going to check it. And, yes. 27. Sigma of 27. Which is equal to what I call the prime power identity. Which is equal to sigma of 3 to the 3. So whenever we have a positive integer from positive integer land as an input that's a power of a prime, it has a very special form. And that is 1 plus 3 to the 1 plus 3 to the 2 plus 3 to the 3. Which is equal to, in this case, 1 plus 3 plus 9 plus 27. Why am I messing this up? No, that's correct. 27. 26 plus 3 is 29, 39, which is equal to 40. And we cannot break this up into sigma of 3 times sigma of 3 times sigma of 3, because sigma of 3 is one more. It's a prime, so 4. That would make it 4 times 4 times 4. Well, that's 4 times 4 is 16, times 4, that'd be 64, right? So we see that 40 exists within the Sum-of-Divisors function because of the form, the powers of primes, form within the function. And then again, this supersedes the fundamental theorem of arithmetic. So, just because we have primes that do not exist does not mean we will not see the outputs of those. We won't see products or sums, depending on which way you get, right? Basically, elements does not mean we won't see elements that don't contain those primes. However, the reasons why we see those elements are because of the two rules, and I could only find two that supersede the fundamental theorem of arithmetic, and that is the prime number identity, which is the prime plus 1, and the power of prime identity is what I'm calling it again, which requires us to add the powers of a prime up to that power, and that creates results that shouldn't exist but do, such as 40, right? 40 is 8 times 5. 8 exists, is an element that exists. 5 does not exist. And yet, if we reverse engineer this, right, what we get is we don't get the number 27. We get the wrong number, right? Well, and we can't even reverse engineer it because 5 does not exist. So there's no way to reverse engineer it. We can reverse engineer 8. 8 is derived from 7, right? So 7 is the 1 factor. But 5, there is no equivalent. So we cannot reverse engineer this multiplicatively. We must use the power form in order to reverse engineer it. So those are the two rules that govern elements within the Sum-of-Divisors function that do not exist. Counterintuitive, and yet consistent. Once we consider what is actually happening, we see consistency. So, let's now look and consider the fundamental theorem of arithmetic governing the elements that do exist, right? So, rule number 3 is, and I messed up, I didn't finish it, but just rule number 2 has an exception, and that is, except when, right, for any pair of primes that are not outputs of the Sum-of-Divisors function, the composite product n will not exist, except when the output, -1, is a prime number, or when n is derived from the Sum-of-Divisors of a prime power, p to the k, right? And we saw both examples. 20 is a result of the prime number identity, and 40 is a result of prime powers. So, moving on to rule number 3. For any factor or element, right? Because we're considering this set, right? The set of all sums produced by the Sum-of-Divisors function. For any factor, pair of numbers that are outputs of the Sum-of-Divisors function. A composite number exists. So, let's see if this holds. See, we have the prime number 3, prime number 7. 3 times 7 is 21. 21 doesn't exist though, does it? That's annoying. Why doesn't it exist? Well, let's consider. Sigma of n is equal to 21, which is equal to 3 times 7, which is equal to sigma of 2 times sigma of 4. Which does not equal sigma of 8 right? So sigma of 2 is, there's no solution for sigma of 2. Or no, I'm sorry. No, yeah, sigma of 2. So 2 times 4 is 8. It's sigma of 8, which is equal to sigma of 8, allegedly, right? Then we do sigma of 8, we have sigma of 2 to the 3, which is equal to 1 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3, which is equal to 1 plus 2 plus 4 plus 8, which is equal to 15. 21 does not equal 15. What's our problem? Same problem as we had with 40. This is derived. 8 is a power of a prime. And so the power prime form dictates that you can't split it up into two parts like this. So the number 21 has no multiplicative solution. It cannot be expressed through multiplication within the sum-of-divisors function. Therefore, it does not exist. So we need to add an exception, except when the pair corresponds to a product of powers, to a product of powers of the same prime. Within, to be explicit, this set of all positive integers. Right? So that means the input. So when the input is made up of two different things, right? When we reverse engineer this, right? So again, this is reverse engineering. There's no longer context that defines this, but rather it's the very structure, right, of the multiplicative form. Once again, we see consistency even though it doesn't make sense. We would think that based off the fundamental theorem of arithmetic, 21 should exist, but it doesn't. And it doesn't exist because of this. And you'll find that every number that doesn't exist is either power prime or because of something else, right? Like it follows. And what we see is, again, fundamental theorem of arithmetic is followed unless it breaks the powers of primes identity, the power prime identity, the prime power identity, right? So this breaks the prime power identity. Prime power identity is what I'm calling it. And the identity looks like this. Sigma of a prime to the power is equal to 1 plus p to the 1 plus p to the 2 plus p to the 3 plus dot 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 plus p to the k minus 1. Well, let's do minus 2 plus p to the k minus 1 plus p to the k. Right? This is what I'm calling the prime power identity. And I have not seen this on Wikipedia either. Like, so this is described, but it's not really clearly named. I don't think. So, and it is an identity for powers of primes, right? This expression tells us what it's going to be. And it's a form, it's a special form of the multiplicative function, right? For powers of primes. And so, right, and so what we're really doing is we're multiplying powers of primes, so we're multiplying the prime power identity is then inserted within, right, the multiplicative form, and we have multiples of these prime powers that are multiplied together to create actually valid outputs of the Sum-of-Divisors function, which consists of these elements. All right? So, rule number 4 is relatively simple. For any prime P that is an output of the Sum-of-Divisors function. Powers of P will exist. P will exist. Right? Let's consider that, right? So we have consider. What I have to do is look for our prime. The first prime is 3, so consider 3. Consider 3. Okay. 3 to the 1 exists. 3 to the 2 is equal to 3, which exists. 3 to the 2 is 9, which doesn't exist. 3 to the 3 is equal to 27, which doesn't exist. 3 to the 4 is equal to, what is it? 84? Is it? No. 74? 60. It's 27 times 3. Oh, 81. I'm sorry. 81 does not exist. Odd. That doesn't make any sense. What about 7, right? Next prime, 7, that exists. 7 to the 1 is equal to 7, okay, that exists. 7 to the 2 is 49. 49. That doesn't exist, does it? What's going on here? And 7 to the 3 is outside of the scope anyway. And that would be 49 times 7. I don't want to do the math. So, point is, it doesn't exist. What you notice is, first thing, is powers of primes are odd. So all these odd. So they're never preceded, aside from 3. 3 is the only exception. They're never preceded by prime. So they don't exist because of the prime identity rule. Well, what's going on here? Well, it's really simple. We go back to our prime power identity. Let's do 27. The sigma of n is equal to 3 times 3 times 3. Well, that would have the form sigma of 2 times sigma of 2 times sigma of 2. And of course, this does not follow our rule, which would be 2 times 2 would be sigma of 8. But we know, both from the multiplicative form and from, right, the nice thing is we can always check the additive form, right? The additive form always gives us the correct amount. So all we have to do is check, and sure enough, we know that sigma of 8 does not equal 81, it equals 15. So we see that for any prime p that is an output of the sum-of-divisors function, powers of p will actually not exist. So yes, I miswrote it originally because I wanted to follow the fundamental theorem of arithmetic, right? Right? And what it implied. So these 4 rules are the rules that govern the multiplicative form within the sum-of-divisors function. So what can we understand from this? What we can understand from this is that perfect numbers, at least even perfect numbers, the ones we know about, are the result of something really interesting. They're the result of a power of a prime that shouldn't exist right? Observations, right? So what do we learn? Perfect numbers within the sum-of-divisors function are the result of powers of a prime that shouldn't exist when preceded, I'm going to say directly preceded by a prime. That shouldn't exist. If you think about it, primes have this identity where every prime plus 1 is its identity within the sum-of-divisors function. So the fact that primes exist, the fact that 3 exists, is an exception because 2 is a prime right before it. The fact that 7 exists is the result of a power of a prime, is the result of the prime power identity, right? 2 to the 2, which is 4. 31 is the result, is the same thing. It's the result of a prime power, right? And it precedes the number 32, which is the power 2, which shouldn't exist. So we see that within, what we have is 2 to the k, minus 1 times 2 to the k, where this is prime. Right? And we'll specify this is for all even. Within, right? Within. Now, let me, so that's one thing, and then the next thing that I want to highlight is what we have shown, have demonstrated, beyond any doubt, is that two to the n is an invalid expression within the Sum-of-Divisors function. Because it implies it does not follow the rules governing the multiplicative form of the Sum-of-Divisors function. In this way, we can understand that the identity, sigma of n is equal to 2n, when n is perfect, is an invalid identity, which is something that I've mentioned and proposed and presented over and over again, right? It's a useful heuristic. It's useful as a heuristic, but it is neither logically valid nor adheres to the rules that govern the multiplicative form of the Sum-of-Divisors function. And what we must understand from this is really, it's not precise enough for what we need. Again, it's a nice heuristic, but it doesn't tell us, it doesn't give us this form, right? This is the form for all even, right? Look at how nice and clean that is, right? And it's really, again, a power of prime number 2, minus 1, and there we go. Look at that, right? Power of the prime 2 minus 1 is a prime. Power of prime 2 minus 1 is a prime. Power of prime. So, and what we get here is this almost perfect square, right? Notice that we get this almost perfect square. All right, I'm going to wrap up this section. So hopefully this has been enlightening. It was definitely very interesting for me. I was really happy because what I found was we established by outlining the rules, defining them, we established consistency within the function. And this is one of the most important things, right, that we consider in mathematics, when we deal with mathematics, is we look for consistency. And what's interesting is it looks like this set of elements is full of contradictions and doesn't follow any rules. But in reality, it's extremely consistent. You only need to understand two properties, right? So we have this additive form, and then we have the multiplicative form. And the multiplicative form is governed by the fundamental theorem of arithmetic, and then superseded by the prime number identity and the prime power identity. That's it. Those two things are what govern the multiplicative form and supersede the fundamental theorem of arithmetic. All right. So next video, I want to explore the sum-of-divisors function geometrically. So I want to look at the positive integers, and then we're going to look at it as actual objects and shapes. And I believe this is really helpful in understanding exactly what we're doing, because what you'll realize is, as I realize, is that really this function is a transformation. It's transforming objects from one shape into another, right? So that's what we're going to explore in our next video. All right, thanks for joining me.